Can you hear me?
I can hear you.
Good. How are you today?
I'm all right.
Okay. How shall we talk? Do you have any idea?
Physics.
Physics? Okay. Do you want to study relativity? Have you heard of relativity, special relativity, or general relativity? Yeah. Do you have any question about the relativity, or do you know anything about the relativity? Time dilation, you know time dilation?
Yeah,
You have time dilation.
slows down as you get faster.
Yes. Okay, can we talk about relativity today?
Sure.
So basically, there's a timeline here. Perhaps to give some history, because one of year 12 students is doing special relativity with me at the moment. So I can probably just pop up some of the ideas. So long time ago, so I think in ancient Greek, and the people don't know how to explain light, right? And guess what they think? They think light is emitted by eye. Have you heard of that ancient Greek people, or even earlier, ancient say Egyptian people? So they say that's long time ago. Let's start from some background here. So basically, it says the people yeah. Yeah. So basically, say if you someone just saw the object here, and they think that it is the light must be emitted by the eye, like a cannon, like a gun, right? And then reflected. Okay, so that's a very ancient concept of the light, right? Of course, that will sometimes explain something, but in many cases, they got trouble. Okay, so don't know what is light. So basically, they're curious about light. But other people will say, well, perhaps light just come from the object of the like sun, for example. That everyone knows during the day, you get shadows. You get a shadow. Okay. Yeah, that would be first understanding that the light travel along a straight line, so that we don't know what time can be considered as the beginning, but we know that before ancient Greek, people realized that so light travel, so light travels along a straight line. Do you think so?
Yeah.
So nothing wrong with that, okay? But if so, because the topic travel, the immediate question is, how about the speed? But the speed, how fast the speed?
How
about the speed or velocity, speed?
Isn't the speed of light like 700 million meters per second?
Millimeters per second. Can we use the international system? I can write down this is denoted by C. I can just use a white card, this one. So it's C. So C will equal to approximately 3 times 10 to the power of 8 meters second. Did you say millimeter? If you use millimeter, what would be the number here? If you don't use a meter, what would be the number if you use a millimeter? So you need to convert this unit, right? If you're talking about a millimeter per second, how to convert that?
That would just be times 1,000, so 3 times 10 to the power of 11.
So 1 meter is much smaller, right? So that's right, 10 times 10,000. So that would be 3 times to 10 to 11. Do you agree?
Yeah.
Okay, is that the number you are talking about?
Yeah.
Yep, that's good. Well, if you use millimeter, but in the physics, we use the so-called international system. It's a united system where all the lengths or distance are the unit for that is meters. Okay, meters. But this sounds a little bit abstract. We know light travels along the straight line, a straight line. Okay, not curvatures. But that thing will change. Okay, after Einstein, that thing will change. We probably can cover that. We don't want to go too detail, but certainly we can cover a lot of issues here. So the more easier way to remember to appreciate how fast the light is. So you can imagine if you flash, if you just consider the light, how fast the light can travel, then that number will be, this is Earth, by the way. So there will be the Earth. Of course, light doesn't travel along the surface, but we just, if you could, we just like a bullet. Okay? If the object, or just consider if the bullet travel at the speed of light, and how many turns can they go in 1 second? How many turns? So number of turn, what is the number of turn? Yeah, I put some math during our talk. Yeah. So to do that, we need to know the diameter of the Earth, do we? Right?
Yeah, I think it's what, 5,000 kilometers?
Yes, actually close to six versus
Okay.
6,400 kilometers.
Okay.
Yeah, kilometers. Now, if you convert to international system, just introduction. So in international system, we just use one integers behind before decimal. So we just use the decimal. And how many zero we have to use? If we use meters, is kilometers. So that's 6,000. If we use meters, what would be the index here?
10 to the power of 6, I think.
Good. Your math is good. Why don't you keep learning math? Your math is good, you see. Okay, that's a condition, okay? We got the speed, we got the radius. Now, what is the distance? What is distance per turn? Circumference, or I do circumference. Can we use different numbers? So we need to find the distance, do we? We need to find the distance. Okay. Given time equal to 1 second. Okay.
Yeah.
T equal to just 1 second. 1 second. Now what would be the S? We have to consider S because once we know S, the number. So once we know S, the number we need to, this number will equal to S times 2 pi r. Do you agree?
Yeah.
Okay. That's how we enter the physics, by just use general basic ratios, right? Now, can we work out the S? So what is formula for the S? If the velocity is constant, of course, this is something we have to be talk about a lot today. If we assuming C is always a constant, Okay, actually this is an assumption Einstein made. By make this assumption, Einstein got invented his special relativity. Of course, here we just trying to solve this problem. Okay, we assume C is constant because we know that the formula for S can be worked out. What is that? What is the formula for S if we know the time and the speed? So what is S? What is the formula for S? If you go to say, if you drive a car, you know, the speed is 60 per hour, slowly, okay? 60 kilometer, and you drive to say 1 hour. What is distance? How to work out the distance?
60 kilometers.
Yeah, what did you do? You use the speed time, the time, agree?
Oh,
You
right.
agree? Yeah.
S means distance.
That's S for
Right,
distance.
okay.
S for distance. So this is distance. So this distance traveled. How much? Then you can work out S. Can you work out S? Can you write from your side or not? 3 times. Can we use international system? So this will be 8. Are you able to write this time?
Let me check.
Yeah, you can use annotate note.
No, I cannot annotate.
You cannot. Okay.
Yeah,
Did you find this choice? Did you find that annotate? You just found the tool. Sliding. There's a sliding.
yeah, I've got the annotate bar up. But
Yeah.
I can click draw.
Okay.
And select stuff and it just doesn't draw. Okay, it's selected eraser automatically, which is strange because I didn't select eraser.
Oh, okay.
Okay, it appears I cannot use anything other than the eraser.
Oh, I see. You use black color. Okay, that's why. Can you change the color to white or to night, say yellow or any other than black? There's you can use the pad to choose to select a color for pen. Can you change the color to say yellow or white or blue or red?
There we go.
Oh yeah, here we go. Good. Now, can you finish this rest? What do we have to time? What is time? What is the time here?
Time is...
Condition is given.
1 second.
Yes, 1 second. Time is 1 second. Yep.
Yeah.
So what is distance?
Distance is...
The same, right? Just the same. Just the same. Of these numbers. So 3 times. If you can write, you can participate. Now, can you work therefore, what is n? So that way we got this, therefore we got a number of turn. N is number of turn. So n is the number of turn. Number of turn of the 10 per second. No, if you can you write?
It appears to be around 7,000, although I know that's not correct.
Okay, can we just write the formula here?
I think it's 7.
Yeah, 7,000 or 7. Can we just do that one? S divided by 2 times 3, 1.4 roughly. Okay, what is R? R is 6.4 times. Can we use kilometers? That would be use meters. Sorry, that's time 10 to power 6. Okay, did you use this formula? Yeah. So,
no, I didn't use that formula. I used I accidentally put down 10 to the power of 3 instead of 10 to the power of 6, so it gave me something. The answer was 1,000 times bigger than it should have been.
Well, it should be very close to number, but less than 10. This should be less than 10.
Yeah, it's 7.4.
Good, good. 7.5 in my memory is 7.5. Okay. So basically, you can see that light travel indeed very fast. Of course, this number, we didn't know this number until many years later. Probably in ancient time, they have invented some very clever method to determine the speed of light. All right. But one question remains unanswered is that we know that the speed of light is fast. Okay, it's not. Light travels so fast. The question remains the same. So this is unanswered question. So the question here is there's one question. See, is C the farthest in the universe? Have you considered this question before? Any object can travel beyond the speed of light? Have you considered this question before?
I figured that any object that approached it would get destroyed before it made it there.
So impossible, right?
Yeah.
Did you read from science fiction, or you just come out from your head?
I mean, no, I just figured it.
Just by your imagination, right?
Yeah, I just figured that something would happen to it. Like, you know, colliding with atoms so fast that something explodes or something.
Why so? If you have charged particle, see, if you put a charged particle into what is called a linear accelerator. So what's called a linear accelerator is put the charged particle into the alternate charge. For example, this is positive charged particle like a proton. They use proton. So basically, if you put a negative here and positive here, and during that period, they will experience a force forward or toward the right side. Do you agree? Because one part is positive, and so I just use a red card. Do you agree? There is a force. There is a force to pull this object. Can you see? To accelerate this object. Okay.
Yeah, it requires an infinite amount of force.
Yes. Now, if we just yes, that's another thing we have to consider. Where does the mass change? That should be answered. That should be the topic tonight. So if we just finish that, they don't stop there. They just use alternate current. So what do they do? They just continue to that configuration. So next time, and they know the charge particle will travel faster. So they are very clever. They just put this gap longer. Okay, put a number tag because they just alternated at a fixed period. Okay, once the particle enter they finish this journey. And there's the alternate that one. So this become positive, and this become negative. This become positive. Can you see? The alternate that they have switch here. So by the time the charge move into this area, and their velocity increase. You know why? Because it has a force. So the velocity will increase. Can you see? I use a longer arrow.
Yeah.
Now, if you just repeat that for say 1 kilometer or 10 kilometers, what would happen? Certainly, according to Newton's, the speed of this proton will increase enormously, and in principle, there is no limit. Why do we have to consider change of mass? Because in Newton's time, mass cannot be created just because the object is moving. So this is a formula. Did you know any physics at so far? So this is how the velocity can change. So the final velocity will equal to. Do you know this formula? So the final velocity, this is final velocity will equal to initial velocity plus AT. Okay. Or if you call this velocity 1, if this velocity 2, right? I probably just use this one. If you just exit once, this velocity 2, this is initial velocity, okay? And the next time, if velocity 3, you can use this formula. So velocity, so this is 3, velocity 2, AT. Every time we accelerate, so T is time for the proton to pass this gap. Can you imagine that?
Yeah.
So when you pass the third charged plate, this charged plate, they're very clever. They draw the hole here, so therefore they create the electric field. They can, so can you see this type of formula? V3 plus AT. And this continue. Okay, this continue. That will be Vn plus 1 or equal to Vn. I'm trying to create some mass content for you. Can you see this kind of thing? In other words, if you call this, if we call this delta V, okay, every time the velocity of electron increase a little bit, okay. So this is the velocity. This is time. This velocity. I hope you can follow my. So this is velocity. This is velocity. This is a. Can you see that initial velocity? That's V1, V2, V3, V4. Okay.
Yeah.
This is not just the time. This not V. Sorry. This is not the velocity. Velocity should be the height. What can I do? Can we call this number? This is this time. Okay, this is a 1, this is a 2, 3, and 4, and 5. So what would be the velocity look like? So velocity were in this moment, velocity this much, right? By the time they reach 2, they just added something. You added something, and you got an interval here, and then they added the same interval every time. Added same interval. Can you see?
Yeah.
That's why you see that velocity increase linearly. So that's called partly for this reason, it's called a linear accelerator. Have you heard of this term? This is called a linear accelerator. So in other words, the speed of the electron, proton, any charged particle, will increase enormously, can you see? So there is no end. If this is C, can we just say this? We just assume if this is C, Newton's law say, if you continue, and the speed of the charged particle can easily go over, can catch up, or can take over of the light. Can you see? Do you know this? Do you understand this diagram now?
Yeah.
We just assume originally, so probably at the beginning, it's just a quarter. We're dealing with a fast charge, traveling fast, which is 1/3 of the light speed, right? After several times, they can easily reach to the speed of light and then go beyond. So in principle, in physics, in principle, no one can stop you if we keep doing this acceleration. Eventually, the velocity of the, in this case, is proton, will go faster than speed of light, than the light. You agree?
Yeah.
Now, answer me. So why do you think that something go fast enough will be destroyed? Why? Because air resistance? What is the reason?
Well, not necessarily air resistance, just like...
Yes, go on.
There's nowhere that doesn't have any matter.
Yes.
Plus, I assume it would...
We say, if this just consider, if this is the sun, okay? If this is the sun, this is Earth. Do you know how many times, how long does it take for the light to travel from the sun to Earth?
About 8 minutes.
Yes, 7.5. Very interesting, right? The minute, 8 minutes, that's right. So consider if this is, we just accelerated the, this is the sun, okay? This is, we just hypothetically, they have charged particle from the sun, tiny particle. There are many tiny particle, like even the electron, okay? It could be electron, could be a proton. Do you know any other particle? Like a muon, it has do you heard of muon? They got, they have pion, they have pi. There are many particles. It's called cosmic ray.
Yeah.
Called cosmic ray. It's called cosmic, right?
Yeah.
Cosmic ray. So that's basically radiation. Now, if we just imagine we have accelerator like we just draw there, right? If we just assume that this charged particle has been initially, I'll get you a different color. So that is initial velocity just left the sun, okay, just left the sun, okay. Now, because between the Earth and the sun, there's no air, so it's actually a vacuum, okay? So there's no air resistance. So that's why I'm asking you, there's no resistance at all. It's just like a vacuum. So if you just hypothetically assume that this will just speed them up, if you just continually speed this particle, then there's no way to stop us. Of course, that's based on Newton's law, not Einstein's law. Let me see. What am I going to do? I'm going to draw the particle here. So if that goes that far, so that by this time, the velocity of the electron will go beyond the speed of light. Do you agree? Or any objection?
Yeah.
Because according to our, because to the previous graph, we just want to draw the previous graph here. What you have is that you got, you know, there's no one, because as long as you can continually accelerate electron, the velocity of electron will simply increase, depending on the acceleration, okay? So if just say if acceleration, this is acceleration small, this is 0, okay? If this horizontal line, it will be 0. If acceleration is large, the gradients increase or slope change, all right? I'm trying to incorporate some math or physics in our talk.
Yeah.
So that would be, that's velocity, okay? That would be the time taken, okay? Perhaps at the beginning, they just probably the cosmic ray or the particle charge from the sun is just probably just a quarter of the speed of light, because light is heavy, because these particles have mass. You are right. You are right. Okay, that's at first. So there's no one. So if this is C, if this is a C here, after a certain time, in this case, we know that by time t1, and the velocity of this charged particle will go beyond the c, the speed of light.
Yeah.
Do you want to make any remark? Do you want to make some comments on this explanation? You see, even in physics, there are like mathematics. There's a basic assumptions, okay, assumption which is determined the nature of the outcome. Are you interested in philosophy?
Philosophy.
Yes.
Kind of.
Yes. So basically, no matter what you do, either in math you have axiom. Do you know axiom? Axiom. Or in Kant. Do you know Kant? Have you heard of Kant?
No, I have not.
Kant is a philosopher in German philosopher in the 17th century, 18th century, right? And he introduced a priori, so that this priori, this Latin. Priori and axiom is very similar. So Kant is in his book. You probably can Google that. That's a critique. I think critique, right? On reason. Have you heard of this book? A critique on reason. Yeah. And in his book, they mentioned this word several times, a number of times. His argument is that no matter how sophisticated our theory or understanding is, one can always go back to trace the very first assumption, right?
Yeah.
So in this case, of course, now we know that it is reasonable, or actually it's experiment confirmed. This is something different from philosophy. In physics, you have to, if you have assumption, better to be confirmed by experiment. So that is different between physics and mathematics. Now, in this case, if someone tell you, okay, if say if, okay, if C is the indeed, that is another one make this claim, okay. C is the fastest.
Yeah.
So what would you say? Then you have obliged to say that it's impossible. This acceleration, as this accelerator, is impossible. Instead, you have obliged to you follow this different. So even you are accelerated, you have accelerated. The speed cannot go beyond velocity, light speed. All right.
Yeah.
Now, the question is, in the history until Einstein, whether we should take this as a claim or truth. The difference between the claim is just, it could be very subjective. Well, sometimes it sounds very reasonable, like some ancient philosophy. Do you know Plato, Socrates, Aristotle? Do you know this guy? No? Some
of them, yeah.
Yeah, Aristotle, of course. Aristotle is very famous. Aristotle. Anything about him?
I don't actually know much about him.
Plato, how about Plato?
Plato, I don't actually know much about any philosophers. I just know what their names are.
Well, I'll tell you what. If that is an open, we can. Plato's contribution is in many areas. Okay, in Republic, you have the famous book Republic. Okay, he concerned of how to build the ideal society, how should be the government structure looks like, and how should raise children, how to improve the stability, prosperity, economy. Okay, they have also the arts. You're also interested in arts. But also, Plato is very concerned about the fundamental questions such as what is the elements of matters. So he came up with this idea. Now, today we talk about, are you in year 9 or 10 now? Year 9?
I'm in year 8.
You're still in year 8. Oh,
yeah.
So you're okay. By the time you go to year 9, your textbook will talk about this one. It's called Platonic. Yeah. Do you have Platonic sonnets? Have you heard of that?
Yeah.
You do. How about this one? This is a tetrahedron made by 4 equilateral triangle. This is one of them. Tetra. What is tetra? What does tetra mean in terms of number? Tetrahedron. Tetrahedron is a tetra, which means 4. Okay. Plato believes that ultimately, unlike the atomic ideas, Plato says that everything, all matters, water, gas, fire, and anything. Of course, Plato believes that there are 5 elements, by the way. Plato believes 5 elements. All of these eventually lost their substance nature, and only the remain is the form. Okay. These basic form contain 5 of them. Another is cubic. This is very symmetrical. Okay. Another one is called is a little bit. This just to make a 2 pyramid. Can you imagine 2? This is I draw the square here first. So you put a pyramid here, and you imagine there has reflection. Okay. So this is cubic. This is the cubic, right? Is a cube or just kill the cube, right? Let's just kill the cube, right? Kill the cube. Is my writing too small?
No, I can read it.
I can read it. The third one is called the octahedron. Octa?
Yeah.
Octahedron.
It's got 8 sides.
Yeah, that's right. Hadron. So that octa is actually means 8. It's like 8 sides. You can use two pyramid back to back or bottom to bottom, right? You can create that. So there are four. There are others. There are others. So they have the another way is we can talk about the next. They have other two. Okay, it's also symmetrical, not a sphere. Okay, so one of them. The reason I talk about one of them is called the ether. Have the ether? I read it already.
Yeah.
What is ether? How much do you know about ether? So Plato believes there's an element. So that one has fire. Another called earth or soil. Earth. It's called 5 elements theory. Ancient people. Air. Can you imagine others? Water. Do you agree? Water. Do you agree?
Yeah.
And anything else? 4 of them. 5th one is ether. Okay, remember ether is very important.
Yeah.
Relative to relativity. Okay, that is so-called 5 elements. They are related to this. They are related to this one. Actually, fire is very fire looks like the tetrahedron. That's why they call it fire. Would be this one. This element. Cubic. How about cubic? Cubic is associated with earth. And how about hadron? How about octahedron? Is air. Okay, it's air. So the 5th one is ether. Ether is not exist around Earth because in those days they believe that the heavenly body must belong to different realm, okay, other than the universe. That other one, the environment we live in. So therefore, Plato introduced the 5th element called ether. It's called heavenly, where the heavenly body move. So it's equivalent to air to some extent, right? And many years later, by the 19th century, so ether was formally used to describe the media for light in the vacuum. So there's no vacuum. So apart from, because vacuum is nothing by definition, right? Vacuum. So therefore, by the 19th century, 18 something, so that would be considered the media of light, the media of light. Oh, it's too crowded here. Can you follow me?
Yeah.
Ether is old name. Okay, first introduced by Plato as one of 5 elements. Of course, this compared with modern physics and chemistry, this is just too primitive, right? Too overgeneral. However, the name was borrowed from Plato's 5 elements and will be used to describe the medium of night. Okay, so therefore we just return to this scenario. Even there's no air between the sun and earth, but the people still believe before Einstein, actually not before Einstein, before the Michelson-Morley experiment. No?
No.
Okay.
I do not.
Well, if you want to know the history, we can talk about heaps of history. So basically, where are we? So basically, you can imagine, can we use different color? Can we use the purple? I use the purple here. So basically, people think if there's no air, there must be such a thing called the ether. Can you see? Okay. Air is just unique to Earth because we got atmosphere, right? Can we put this yellow dot here? So yellow dot is air. This is atmosphere. You agree? Beyond the atmosphere, there's no air molecule. This is a purple line. They just indicate that, well, they probably have, like I don't have to draw. So basically, the ether is everywhere. Okay. That is why the light of the sun can reach the Earth and other planet. That is the people's common sense. How to say? Do you know that idea when you're talking about the climate change? What is people's many people's opinion? What do you call it? Consensus, right? Do you know the word consensus? Hello? Are you
Hello.
listening? Yes?
Yeah.
Do you know the word consensus?
Consensus?
If people suppose the majority of people just believe or accept something, so what is the English word to describe that? Consensus. Consensus, right? C-O-N? Consensus.
I think so.
Yes, I think that's the key word, because when we talk about climate change, people do this, oh, say, don't argue with me, this consensus. Okay, consensus. Yes, consensus, that's a code word here. Which meaning that majority of people accept or take it for granted. It's called a general agreement. I write down, this is a keyword here, you want to so. Con means common, okay? Consensus is just, you can make up things as consensus, okay? You know this word? Consensus.
Yeah.
So the consensus before, that is before prior to, I guess, that is before, until 18, I don't quite read, I think it's 87. I can put the number, I put the question, yeah, it's very close. This year is special, okay? Because we're talking about how physicists dealing with the axioms. So by that year, people accept that ether is everywhere, okay? So ether is everywhere. Is that logical? Do you accept this claim?
Oh, I mean,
Ether is everywhere. Can you see the dot there? Do you accept this assumption? You think it's reasonable, right? Be careful.
Well, I mean, for an assumption, I think with the information that they had done, that was reasonable.
Yes.
But I know it's false.
Yeah. Well, yeah, that's a story after that year. Okay, that is after Michelson-Morley experiment. Yes. Yes, you can see it sounds very reasonable, because why? Because you know the sun travels in air. Without the air molecule, what would happen? If you two people talk, you know, halfway between the sun and the moon, halfway between sun and earth even. If two people talk, do you think they can hear each other? If you have two people to talk here, just probably 10 meters away, do you think they can hear to each other? I talk about the sun, not the night. Have you considered this question? No,
I have not.
Now, then you're doing experiment. Do you have proper, do you have the small, any object that can make a sound, like electrical, digital stuff, alarm, can you put an alarm? And you just cover with if you have, you need to find a way to, this is air around it, you have to find a way to vacuum it. You can remove the air. Probably have to wait until your teacher gives you this demonstration. So basically, if you put an alarm, a bell, in that in the vessel, then you remove the air, then inside become vacuum. And you wouldn't be able to hear any sound from this alarm. Yeah. Because why? Do you know why? No. Because the sound is vibration of disturbance of the air molecule. The reason we can hear the sound, let's go to the next page. So talking about the sound is a wave. Okay, if you have the bell here, the generator sound, okay? And in the distance, and the people can hear it. Okay, this ear, okay, people can hear it. Okay, so what's happening is that both this is a source, this is a source. Okay, these observers, this observer. Both source and observer are immersed in the air. Okay. The reason we can hear that because originally the air is like this. So this is a silence. However, once the source vibrate, this source vibrate, and they will create this kind of pattern. Can you see? They make this distribution unevenly. So sometimes is density is higher than others. Now, if you just this yellow dot is represent the air molecule, right? So if you take a photo, if you just draw a straight line here, if I just let me see, yeah, if I draw a straight line, yeah, that's the distance between the two objects. One is a source, and the vertical line will use the density, air density. The vertical line will be called air density. Okay. Do you know this letter in Greek? We use no rho to represent air density. Density. How to define the density? Do you have concept of density?
Density.
Yes.
I don't know how to find density.
That is mass per volume. All right. So for example, different material have different density. For the metals, the density is extremely high. But for for the other things like like timbers or other even the vegetables or bananas, this density is much smaller. Do you agree? So that will just count how many particles, how many atoms per unit. Okay, so this is just counter. So this is a lower density, and this is a higher density. You see, this is a higher density. So it depends on how many mass, how many molecule in the given molecule. This is high. So one is, so this is high. This is lower density, lower. So low is not. This is high. Okay. If you follow this definition of density, you can imagine. I will draw the picture now. So between the sound bell, between the bell, this is the bell, this is ear. Okay. So this is x to this denotes the distance. If I choose the color, if you use say the orange color, it'll be fine. So you will notice that if there's a sound, if you could take a picture, you can map in the density. The density will be oscillate around the equilibrium. Can you imagine that? Yeah. And the next moment, it will move. You will move forward. Okay, I just draw another one. This time I use a solid line. Can you see?
Yeah.
Yes. The solid line means a moment later. So that could be said. It could be. So this one is a t0, t equal to 0, and the solid line will t equal to 1 second. Depending on how fast the sound travel. This is how the sound travel toward that. The speed of sound will just use v, which will be different from c. By the way, do you know the sound speed, roughly, compared with speed of light? Sound speed. Supersonic. You know, supersonic, nowadays, almost all commercial jet is supersonic, which means the velocity is faster than speed of the sound. But do you have in air? In air, you have mentioned that in air, because the sound speed change if you travel at a different medium, for example, the sound speed in timber or in the steel will be very different. Do you have any idea about the number of sound speed in air?
Sound speeding out. I think it's like 340 something meters per
Yes,
second.
very good, very good, very good. Yes, it depends. Yes, very good. 340. Yeah, that's meters per second. Okay. Now, how about this in air? How about the velocity in the steel? Air and steel.
I think it's. I don't know.
Yes, over say 6,000 something. Much faster.
Yeah.
Because the velocity is dependent on the density. Okay, the higher the density, the higher speed. Anyway, to cut the story short, so this is called the move. This is called the motion. This kind of move is called the motion. Is wave. This is called the wave. It's called the wave motion. So wave move. So sound and is one of the wave. So the sound. So both the sound and the light can be treated as a wave. So that is a mechanical wave. So it's air density or the density of matter is called mechanical wave. How about light? Have you heard of what is our modern interpretation of the light? It's a wave, but what a specific wave? What is adjective here?
Isn't it like
It's very
it's
few.
both a particle and a wave.
Oh no, we don't go that far. We don't go, that's quantum mechanics. You know, okay. when you start physics, there are several things you need to consider. One is force. Another is heat. Okay. Another is sound. These are natural phenomena, and that one will be light. So fourth one will be light. Apart from that, any other natural phenomena, can we put that into the similar category? I'm going to talk about the natural phenomena. So natural phenomena. Anything else? Force, heat, sound, electricity.
Yes,
electricity. Yes, of course. Anything else? Do we take into the associated magnetism as well? Because last time we talked about,
yeah.
That is probably when first built the building of classical physics. They start from this 1, 2, 3, 4 or 5 elements. Okay, or it's not elements; these are 5 phenomena.
Yeah.
Yeah. Of course, force is associated with mechanical motion, but eventually they take years before people realize the electricity there is and magnetism belong to the same thing. Okay.
Yeah.
And it take another perhaps until Maxwell, and they realize that no, that will include light as well. Can you see? They unify the phenomena. Before that, people will think that is, the phenomena can be divided into 5 different categories. It's take about 200 years for people to realize that the light, electricity, magnetism belong to the same thing. It's called magnetical. Thus, this adjective will be electromagnetic. I like the idea you mentioned that the dual property of light, and sometimes we have used a particle like photon, right? To be specific, it's photon to describe the light. Is that what you mean?
Yeah.
Yes.
Yeah.
That's right. Yeah. But before that, we have to understand. Wave is a good model to describe the light, or this is called electromagnetic wave. So that is that's full name. Is electromagnetic wave, like a radio wave, okay? For example, we have the radio wave or RF wave. Do you know RF? It's called a radio frequency, R for radios. Of course, more familiar with microwave, a microwave. Do you know microwave? Microwave, you cook every day. Do you use microwave? So this is also that electromagnetic wave, but it's invisible. Any other wave, electromagnetic wave, you can imagine? Any other electromagnetic wave, they have proper name, apart from microwave? If you go to hospital, you have trouble with your lung, what doctor would do?
Like an fMRI or an X-ray.
X-ray. MRI, I'm not making MRI. MRI is RF, plus magnetic field. We're talking about that, if you are interested. Because I don't know, you see, we can talk a range of many areas we can discuss, okay? Because at your age, you are curious about a lot of things, okay? That's very important. Keep that curiosity and ask a proper question, okay? And then you can explore more, and eventually you will decide what to be studied. All right. Any other thing apart from X-ray? Any other ray you are aware of or have you heard of? How about the radiation from the nuclear? What is the ray we call it? There's a special ray for nuclear radiation. They have proper name. Think about it. Greek letter. What is third? What is third Greek alphabet? So you got alpha, right?
I think it's gamma.
Yes, gamma. Yeah, that's gamma ray.
Beta gamma.
Have you heard of gamma ray? Today
yes.
we know a lot of ones. So what's the difference between gamma ray and X-ray? Is a rho, pronunciation rho, is a gamma. Gamma, right? Is a beta, is alpha. The English words, alphabet is come from this one. Do you know the word alphabet, of course? Alphabet, okay? Alphabet is combination of these two words. Well, gamma ray, what's the difference between gamma ray and X-ray? And also, more importantly, what is night? What do we call the night? What is the nickname for the night? How many words?
Know.
Oh, you just think about it. No. How many? Say, let's just go to next page. A little bit crowded here. So talking about the ray, how many? We just probably today we end up with this introduction for electromagnetic wave. That is a spectrum here. I don't use this color. Is that is a white color. Okay, it's called here. So this is a spectrum we often use. It's called electromagnetic spectra. Okay. Colors, you see the red color. Okay. And you also the yellow color. And also before that you have the origin. You have the origin here. So these are colors. Anything else? Blue colors, okay, blue color. Or green before that, I have to make it green. Have you seen these patterns before? And the purple or violet. Okay.
Yeah, it's spectrum.
Yes, spectrum, electromagnetic spectrum. So the full name is that if you just consider this is the wavelength. This also another Greek letter called lambda. Pronouncing lambda. So lambda is the wavelength. That is wavelength. Oh, sorry. Wavelength. Have you heard of wavelength?
Yes.
Yeah. So this part, this crowded place, is made a contribution by Newton. Okay, Newton doing experiment. They just say the visible light is called the visible light. It's called the visible light. Visible light, right? Because Newton first did experiment to separate the white light into different color, right? So this is visible. How about this region? How about this region? What do you have proper name?
One of them's ultraviolet and the other one's
Ultra, yes, that's UV. It's called
infrared.
UV. And is this what?
Infrared.
Infrared, yeah. Infrared, yeah. So where's X-ray? Where does X-ray go? Which side? Which is microwave? Which X-ray? Left-hand side or right-hand side?
I think microwave is part of the infrared light.
Good. Beyond, yes, it's very overlap. Yes, right. It's got microwave here. It got actually radio wave. It's got a microwave, so that's microwave. That's microwave. Good. Where's radio wave? So for microwave, the millimeter lambda is about 1 centimeter. Do you know the American want to adopt a very powerful radar? It's called X-ray, X-band. Have you heard of X-band radar? X-band radar. Have you heard of X-band radar?
No, I haven't.
Because that is anti missile. Okay, so if someone not there to launch the missile, they can immediately detect it. All right. And this band, that is microwave. So the lambda is a few centimeters. Oh well, we'll continue next time. You see,
All right.
As long as you are interested in something, in science, in natural science, even including philosophy, we can talk. All right. So today we're just the beginning of our study of light. Eventually, we'll go to Einstein's idea. Okay. Have a good time. Goodbye.
All right. You too. Goodbye.
Goodbye.